Hello, this is my Physics 2212 Lab 5, and in this experiment, the purpose of the lab was to demonstrate induced current and Faraday's law by collecting the time data of a magnet falling through a conductive tube of aluminum foil. The physics principles I used in this lab were Faraday's law, Lenz's law, Biot-Savart law, Newton's second and third laws, and the time derivative of the magnetic flux. As you can see, some of the formulas I used were here. And the result of the experiment were that my experimental time came out to be 1.248 seconds, while the computational time came out to be 1.239 seconds. The model was that the bar magnet acts as a magnetic dipole while falling through the tube of aluminum foil, and the assumptions were that the system is isolated so that there is no other magnetic fields that can interfere with the system. The magnetometer app accurately defines the north and the magnet. For the experiment, we have the system, which is the magnet, surroundings is the aluminum tube and everything else. The initial conditions were the magnet and tube of aluminum foil at time step 0 and velocity 0 is dropped from rest. The details were that we wanted to determine which side of the magnet was north. We wanted to measure the length of the aluminum foil tube, and then we wanted to drop the magnet through the aluminum foil tube and then find how long it took for the magnet to fall through the tube. For the experiment data and results, for the tube of aluminum foil, we have our length, width, inner radius, total radius, and for the magnet, we have the massive magnet and the magnetic dipole moment, which is calculated from the Biot-Savart law, and the times we have right here for our time travels, and the average time we got was 1.248 seconds. For the checkpoint questions, why can't we use a ferrous tube, for example, like a steel pipe? We can't use a ferrous tube for this experiment because a ferrous tube contains iron inside of it, which has a strong magnetic property, and this would make the tube create an induced magnet, and that would interfere with our experiment. And what happens to the magnet? How does this compare to the magnet falling in free space without a tube? The magnet falls slower through the tube in free space because the tube exerts an upward force to oppose the change in flux for when the magnet is falling through it. For our coding, we just have, for step 1, we have our mass, the mu of the magnet, and then we have our dipole B for step 2, which is calculating the R mag, the R hat, and then putting that into the B formula, magnetic field formula. And then for step 3, we're calculating magnetic flux. As you can see here, we have the radius of the ring, the distance, the speed of the bar magnet, the numerator and denominator of the df/dt, and we just divide the two to get the flux. And for step 7, we just have the force of gravity, which is just negative of mass times gravity. And for step 4, we just have the ring of current, which is just the flux dt over the ring of R. And for step 5 and 6, we have the magnetic field at the ring, which is equal to the dipole function, and we have the B hat value, which is just calculating the unit vector of B, and then we have the sine theta, and the magnitude of F on ring, and the magnitude of F on magnet, which are calculated here as well. And then for step 7, we're just calculating the net force, and for step 8, we're just calculating the velocity and position of the bar. Here are the results. Here's our velocity versus time graph, and here's the time down here. For interpreting the simulation, the color of the tube indicates that the current with the color being in different directions. The blue is clockwise, while red is counterclockwise, and we do this through the application of Lenz's law as the magnetic field from the induced current opposes the change in flux. When we flip the magnet around, nothing would change, and the magnet's fall would still be slow. The computational real-world system would relatively be the same, and some errors that may have occurred to make the computational system more accurate were that there may have been some unaccounted for air drag. The measurements of the tube may have been off, and the timing of the fall may have been off as well. And the shape of the velocity versus time curve tells us that the force in the beginning was not equal, and they eventually evened out. For the what-if question, if the resistivity decreased so that it was as close to 0 as possible, the current would be extremely high, causing the magnet to fall very slowly. And for the why, if there are holes or slots cut into the tube, there would be less current rings on the tube, and this would cause less opposing force in the tube, and it would turn in turn make the magnet fall fast into the tube. And that's it.